All right, today we have the pleasure of having Diego Mondéjar Ruiz from Universidad San Pablo of Madrid, and he will be talking about approximation of compact metric spaces by finite samples.
Okay, so thank you very much for inviting me for this talk, and thank you for being here. So yeah, today I've been talking about some compact approximation using finite samples that we have been doing, and I'm going to start by the overview. So the motivation of these approximations is similar, or is based in the topological persistence or the persistent homology. So as I told you how the approximations are done, you will see that they have similar behavior than the topological persistence. The idea behind these approximations are based in something called shape theory, which is a kind of homotopy theory that I will explain. And we are going to use finite topological spaces. So I will tell you a bit about these spaces and how we can use them here. And finally, I will tell you I will show you the way we do the approximations and the results we obtain. So we start by the persistent homology idea. So this is the idea that we have in our mind to do these approximations. So we have an unknown topological space, a very easy one here to show you the example. So we have one circle here, S1, and we have a sample, a point cloud, a sample of X. And we say that maybe it's noisy. Here it's very noisy. So, and as we know, persistent homology is very robust to these noisy samples. So this is the idea that we have in mind. And in our problem, we want to determine some topological properties of our hidden space. So we assume that we don't know our space using the samples. So in persistent homology, what we do is that we try to use these samples to construct some simplicial complexes that maybe approach to the topology of our space. So here, for example, we consider an epsilon prime and an epsilon, two different values for epsilon, and we construct the Biot-Rips complexes. And in this example, we see that none of them really approach the homology of our space, right? Because in the red one, we have two holes, one representing somehow our real hole for our space, and one that is representing nothing but just the way the points are sampled. And in the blue one, we have also two holes or two generators for the homology, but we also see that one of them is really the homology generator that we want to detect, and the other one is just noise or something we don't want to detect. So the idea of persistent homology is just to consider the inclusion of the red one into the blue one, and then this is inducing in the homology one map that is preserving only the real hole that we want to detect. So the image of this induced map is set. I mean, is only the generator that we want to detect. So this is the idea roughly of the persistent homology. And of course, we do this not only for two epsilon, but for a whole set of epsilon. And we see how the homology groups survive along the filtration, right? So here, for example, we see that we have one hole here that we want to detect, and maybe kind of one hole here that we also want to detect. So when we do the persistent homology process, what we detect is one hole that persists and another one that is not persisting that much. Okay, this was discovered or developed by several authors, but I wanted to point out here Vanessa Robbins with shape theory, because in her approach, she mentions that, that this is related with shape theory. And this is our starting point for our research and our approximations. So The persistent pipeline is finally this, is just get a point cloud and do a filtration of complexes using Beatrice Reeves or Cech complexes, then apply homology and then get a persistent module, and finally get a barcode to detect the topological or homotopical properties that we want to detect. So now, what is shape theory? When I explain shape theory now, you will see that it's similar in spirit to persistence in some way. So shape theory is something that we want to detect some topological properties of some spaces that has very bad local topological properties. In these cases, the homotopy theory fails and we can detect these properties, and that's why we want to use shape theory. So for example, here we have the Warsaw circle, which is the image of the function of the sinus of 1 divided by x, and we close it and close it around like this. So we are kind of, we have something that is similar to a circle in some way, but it's not really a circle. So when we try to detect the topological and the homotopy and homological properties of this space, we get that all the homotopy groups are 0, all the homology groups are 0, but this space is not trivial. This space, first, is not contractible, and second, and more important, it separates the plane. So we have some structure here. And this property of separating the plane is similar as the S1, as one circle. So what we want to do is to replace this notion of homotopy with another notion that is larger in some sense, that captures some topology here, some not homotopy, but some topology that we have here. So the idea of Karol Borsuk is that the neighborhoods of the space are not that bad. Even if your space is very, very bad, the neighborhoods usually has a good behavior. So for example, in this Warsaw circle, we have that the neighborhood is just an annulus. So something that has the homotopy type of a circle. So it's close to something that for us in this theory, we want to be similar to our circle. If we see a closer neighborhood here, we see that it's also an annulus. So what we have here is that it doesn't matter how small you do the neighborhood, is an annulus, so it has the same homotopical properties than S1. So this allows us to do a theory to compare things like the Warsaw circle with the real circle, with S1. So what we are looking here is for global properties of our spaces for those spaces that has very bad local properties. So for example, here we have the Warsaw circle that, as I said, has the homotopy groups, and the homology groups are all trivial, but it separates the plane. And I want to detect this using some maps with a circle. So the problem here is that we don't have good maps from the circle to the Warsaw circle and go back. So we're going to construct some maps between the two using the neighborhoods. If you see, the neighborhoods of these two spaces are homeomorphic. So for us, it's important that they have the same homotopy type. So we can do a map between both, and the map is the identity in an homotopical. It has the homotopy type of the identity. So we can go further and do a smaller epsilon, and we have the same map. And if we forget about the space, we see that the sequence of smaller and smaller neighborhoods can be mapped between them and with the identity in homotopical terms. So we will say, or we have that S1 and the Warsaw circle has the same shape. We have more spaces. Typically, I mean, the Warsaw circle here is the typical space that we use in shape theory. Also, the Hawaiian Earring is a very common space to work with shape theory because it's very suitable for us. So we can compare, for example, with this set of circles here, and the way we do it is the same. We take an epsilon neighborhood. We take another one, and we see that these neighborhoods, if we just see the neighborhoods, we see that they are the same. So they have the same homotopy type. So we have, in the end, we have two circles that maps into something with one circle here. So when we map these two spaces, we see that the maps are preserving the same circles in both spaces, right? Because here we have that this circle is killed here, so here and here, but there is here one homology generator that is preserved under the map. So somehow we are preserving what we want to preserve, and we are killing the same stuff in both spaces. So these two spaces has the same shape. But shape theory is not only about how many circles can I draw on the plane, but the maps. How can we map the neighborhoods into the epsilon neighbors between them? For example, in this space, if I take an epsilon neighborhood, they are two annulus. In the next step, I have three annulus here. And the problem here is that if I forget about the space and I separate the epsilon neighborhoods, I see that I have the same annulus in both spaces. But when I map them, I have that here I kill one homology generator. Here, this homology generator is killed here. But in the other space, all the homology generators maps into another homology generator. So I'm not killing the one that I'm killing here. So in this way, we have shown that these two spaces have different shape. So shape theory is very important. For shape theory is very important the functoriality. So how we apply maps, and this is what I was telling you about the similar that it's similar to persistent in this way, right? Because we use how the topological properties or how the homology generators, for example, are preserved under the maps that we have. So the problem with this shape theory is that in this way I explain it is very hard to formalize, because the way this is formalized is to embed the space into the Hilbert cube, and then we consider sequences of maps between the neighborhoods, and then we consider a notion of homotopy and a relation. In the end, when you have when you have defined the morphisms that we want to add to our homotopy theory, we have that is not very suitable for work, because in the end, what we want to do here is to create some invariants and then be able to compute the invariants for our spaces. So in order to generalize for not only for compact metric spaces, so to more general topological spaces, and to apply this to compute invariants, we need different approaches. So in the end here, what we are doing, if we think a little bit, is to approximate our bad spaces like the Warsaw circle with good spaces. And when I say good spaces, I mean this annulus that has the same homotopy type that a circle. So in some sense, I'm approximating the Warsaw circle with S1, right? With a sequence of maps between something that has the homotopy type of S1. So how can we generalize this idea in a way that we can compute things? And the answer here is the inverse limit. So with the inverse limit construction, we can do this. So if we have a compact metric space, we can always represent X as the inverse limit of an inverse sequence of compact ANRs. So here I say ANRs, but you can think about polyhedra or CW complexes. All them has the same homotopy types. So we can use any of them really. But here in the end, what we are going to use is this sequence of compact polyhedra or ANRs to approximate X. So X is going to be the inverse limit of those spaces, and we can always represent X as this inverse limit. The problem is that this construction is very theoretical, and something that we have done here, I will tell you later, is try to do this in a more computational way. So here I have my spaces represented as inverse limit of compact matrix spaces, and my maps between spaces are going to be maps between the sequences, not the spaces themselves, exactly as I was doing with the Warsaw circle. So this is shown to be exactly the same as Borsuk shape theory, and this is the way we are going to work here with shape theory. So the Cech homology, for example, is the most important one. The most important shape invariant. So is the way it's computed is exactly the way we compute shape, right? Is you consider an inverse sequence of spaces with inverse limit our space, and then we consider the homology in braid K, the homology sequence of groups, and then the inverse limit of these groups will be the Cech homology group of our space. In our example, we have that the Warsaw circle has the same Cech homology than S1. So in S1, we just set the identity because S1 is a polyhedra, is an A and R. So the inverse limit of this sequence is just S1. So the inverse limit of their homological groups is set. But if you recall, we approximated our Warsaw circle using some annulus, so some spaces with the same homotopy type. So here, whenever we find two things with the same homotopy type, we consider that they are the same because shape theory is trying to enlarge this category. So we start from homotopy, and here we enlarge to morphism. So in the end, we have that the Warsaw circle has a Cech homology set as the Warsaw circle, as S1. Okay, so now for doing my approximations, I'm going to use the finite spaces, finite topological spaces. So finite topological spaces are very interesting because the first time you think about finite spaces, or at least me, you think about discrete spaces, and you think there is no topology at all there. But of course, you can set some topology, some interesting topology there. So actually, you can have a lot of topology. And the first thing I'm gonna explain is I'm going to use finite topological spaces, and I'm gonna use the characterization of them as preorders, and if they are T0, they are posets. So in the end, for every set, we have that the finite topologies are just the finite T0 topologies are just posets. So this is very nice in our construction because for us it's very easy to show some theorems due to this property, and due also to the property that functions between finite spaces are continuous if and only if they are order preserving. So we are going to construct some maps, and when we have to prove that they are continuous, this step is very easy because of this property, which is very nice. Okay, so we are going to also use this theorem by McCord that was kind of surprising also to me, because it says that you can reach the same topological groups and the same homotopy and homology groups of every simplicial complex with finite spaces. So for every finite T0 space, we have a simplicial complex that is weakly homotopy equivalent to it. So here, for example, we have our space with 4 points, and we set a topology here, and I choose this topology because this is a non-trivial topology, because actually I get a space here that has the same homotopy and homology groups than S1. So here, this is constructed just using the minimal neighborhoods. So we have that every point in our space has a minimal neighborhood because they are finite. So we just set the minimal neighborhoods, and then we set that the order that define the finite space is just by inclusion. So A is smaller than B if the minimal neighborhood of A is included in the minimal neighborhood of B. Only with this order we have defined the finite topological space, and we show, I mean, this theorem shows that there is a simplicial complex with the same homotopy and homology groups. And the other way around, we have that for every simplicial complex, we have a finite space with the same homotopy and homology groups. Okay, so now, how can we construct our approximations? So we start with a compact metric space, and we know that every compact metric space has finite approximations for every epsilon. So I want to do finer and finer approximations, and I'm going to try to join them with a map defined by proximity. So what I want to do is for every point in here in A prime, which is a finer approximation because epsilon prime is smaller than epsilon. So I want to find a map that maps every point into something here defined by proximity. So what I'm going to do is to define to every point in this space, I map it to the closest point here in the approximation. So, for example, the red point goes to the red point for sure, but for points like X here, the blue point, I define the map that goes to the closer point in this approximation. The problem is when I have 2 points at the same distance, if you have approximations here and here, is very weird than in real examples. You have points at the same distance, but from the theoretical point of view, it can happen, and it happens. So I have to define the maps in that way. So what we do is to use multi-valued maps, or equivalently maps between hyperspaces. So I want to define a map from X to the approximation, and if I have to define a map with points that are at the same distance, what I do is I include a new point, AB, so I map X to AB, to the union of the 2 points. So I'm adding more points, but I can define maps. And this is the... So for every approximation, I define the finite hyperspace of the closed sets contained in my approximation that are not empty and that are closed. And I use them with the upper semi-finite topology. So this is a topology for hyperspaces, but in the end, as I told you, we are working with a finite space, and in the end, this topology leads to the topology defined by the inclusion as sets. So one point is going to be smaller than another if and only if it's included as a set. And I'm not going to consider all the subsets of points, but only the subset of points that are epsilon close, actually 2 epsilon close. And this 2 epsilon is just a technical thing that I need to use. So I consider subsets of near points and this topology here. So one example to understand this topology, this approximation. So I have A, which consists of 5 points, the blue points that are in here, and 4 points that are close, epsilon close, or 2 epsilon close for real. I add a new point. So A and D are very close, are 2 epsilon close. So I put a new point, AD. And same thing with ADB. I add a new point called ABD. E here is not 2 epsilon close to any of the points, so I don't add any red new point here. So in the end, I started from my approximation A, and I finish in my finite space U to epsilon A with this topology. So I have my 5 starting points and the added points, the red points, with the topology defined by the inclusion, just by the inclusion. So I have a very easy topology here and an approximation. And this construction is done so I can map one space into another only by proximity. So I define a map just sending the points in here to the points in this approximation to the set of closest points in this approximation. And this map is continuous. As I told you, it's very easy to prove. I mean, it's not easy, it's just trivial to prove that this map is continuous, because if I send these points to the closest points here, if I have a subset of these points, it's going to be in a subset of the closest points. So it's just trivial to see that this is continuous. And I can do this for every approximation. So in the end, I can find a sequence of real numbers tending to 0, and a sequence of finite epsilon approximations, and a sequence of continuous maps. So from now on, I'm going to say, instead of this U2 epsilon A sub, I'm going to say U sub n for ease of notation. So I can define an inverse sequence of finite spaces. And by the Alexandrov-McCord correspondence that I told you before, the one that transforms finite spaces into polyhedra, I can find an inverse sequence of polyhedra. So the conjecture that is done for this sequence is that this inverse sequence contains some shape information about our space. So it defines, for example, maybe the Cech homology or something like this. So this was our starting point for this research. And we find that we have that this is actually an H-pole expansion of X, that this is the technical way of saying that it represents exactly the shape of X. So we find a very good result for us, because we thought that we have some information about the shape of the space, and we actually have all the information about it, about the shape. So actually also we have all the homotopical information, because shape and homotopy type is the same for polyhedra. So if you are working with polyhedra in the beginning, in the end what you have is the homotopy of X. Now, we, instead of using this simplicial complex associated by McCord, we tried with different simplicial complexes like the Vietros ribs, the Cech, the Witness, and Docker, which is some new simplicial complex associated to this that we use the name of Docker because it's similar to the ones that use Docker in his paper of his famous paper of homological homotopy relations. So all these simplicial complexes turns out to have the same good properties as the one that we use in the beginning. So if we use this simplicial complex to construct an inverse sequence of polyhedra, we get that we also have H-pole expansions. So we recover all the shape properties using any of these simplicial complexes. So we try to compute some of our results, like explicitly to see how can we compute things. So here we have the Warsaw circle here in the left part, and in the right part we have something which has which is homeomorphic to it, and is we call it the computational Warsaw circle. So we want to compute here some approximations in the way I showed you and see how they define the shape of this space. So I mean, the way this is constructed is just because we want to do it by hand. We want to construct the approximations so we can compute the numbers and see what happens. So here we have that for every n, we can do an epsilon n approximation using this formula. The way these approximations are done is we need, for every epsilon, we need that the next epsilon is small enough. That's why we have here these concrete numbers. We can't take any approximation here. So we need epsilon 3 to be small enough. So in general, if I have epsilon n equal to this formula, I have that every epsilon n is small enough for the next one, and I can do the construction, and I can construct the associated simplicial complexes. So what we do here is just to compute the homology of this simplicial complex, which is 3 copies of Cech, and the homology of this simplicial complex, which is 17 copies of Cech. When we map the homology generators of this simplicial complex into this simplicial complex, we see that all the generators here are killed but one. Only this big generator, the one that is representing the circle that in the end I want to detect, only this generator is preserved under these maps. These two are not the maps of any cycle here, and all these small cycles here, you see, all the small cycles here maps into nothing here. They are killed here. So what we have is that the first homology group, when we map one into the next one, we have that the only cycle that is preserved is the big one here. So with two levels, I detect the homology of my space. Actually, this happens for any pair of integers, so I can go further in the approximations, but the important thing is that in this case, I detect the homology of the Cech homology of this space in only one step. So I don't need to compute the inverse limit, which is not possible in examples, like to do it with samples. So we call something inverse persistence to this process. So when I have a point cloud, I can adapt this construction to the point cloud. So I construct a polyhedral approximative sequence, just taking our approximations and some inverse sequence of polyhedra in the way I showed you before. And then we compute the inverse persistent module, just computing the homology groups, and then we have a barcode. So it's just a way of constructing the inverse persistent modules in another way, with this only using some points of the approximations of in each step. So if you recall, let me go back here one moment. So here we obtain an inverse sequence of finite spaces, and then we associated an inverse sequence of polyhedra. After showing that this inverse sequence of polyhedra was detecting what we wanted, we ask what happens with this inverse sequence of finite spaces, like only the finite spaces, what happens in the limit, like the inverse limit. And we found this result that the inverse limit of the finite spaces has the same homotopy type as the original space. And we can find explicitly a subspace of our space, of our limit, sorry, that is homeomorphic to X. So when I do this construction in the limit, I obtain something which has the same homotopy type that forms into a subspace that is exactly our space. And we can, the way this is done, as you are going to see in one example, you can see in the construction who is going to be the subset of which is homeomorphic to your space. So as a corollary, the homotopy types of compact metric spaces are profinite, so they can be reached as inverse limit of finite spaces. So I have a sketch of the proof here, but I think I'm a little bit out of time, so I'm going to sketch the proof to the example. So in the example is an example for the interval 0, 1. Here we start with the first approximation, which is these points, and as I told you, the second approximation has to be with a very, very small epsilon, like small enough epsilon here. For this approximation, the next step has to be this way. So it really, the epsilon it really decreases a lot in each step. But here we can see that for this example, we can write epsilon explicitly as the approximation, and we can write the approximation itself, and we can see the points how we obtain the inverse limit. So yeah, this is related with the proof that I skipped. So let me just tell you that when we do approximations here, we have that the set of approximations always converge to a point of our space. So all the inverse all the elements of the inverse limit in the end are a sequence of points in each approximation that converge to our point. Okay, so what we do is to associate to every sequence one point in here, the point that into the one that they converge, and to every point in here we can associate several sequences here, and that's why this is not an homeomorphism but something with the same homotopy type. So we have a map in here which is like this, and the map associating to every point in here a sequence here. I can take many sequences here. So from all the sequences here, I just select the maximal one. So I can explain this in my example. So here, for example, imagine that I have, for example, my point 0 is very easy, that the way we approximate the point 0 as it is in all the approximations, the point, the element of the inverse limit that approximates it is just the sequence of zeros all the time, because it's in all approximations. If you have points that are in some approximation at some point and all their other approximation, so I have, for example, for points that are like this, so they appear at some point in the approximation, I have that this point at some point, this sequence, sorry, at some point is going to be just the point I want to approximate, because it's in the approximation, so that's it. But for example, here I'm doing the approximation dividing by 3 the numbers, so the number 1 divided by 2 is not going to appear never ever here in the approximation. So the way this number is approximated is, for example, with 0. In the first approximation, in the trivial approximation, I use the 0, but this is, so in the first approximation, I use 1 divided by 3 and 2 divided by 3. So these 2 points. In the next approximation, I use these 2 points. So this, and so on. So for 1 divided by, for half, I use the 2 closest points to approximate it. But it happens that the element of the inverse limit that consists only in the first element of this sequence, so 0, 1 divided by 3, 13 divided by 3 to the power of 3, and so on, only using one side of the numbers, also converts to x. And the same happens with 2 divided by 3, 14 divided by 3 to the power of 3, and so on. So I have 3 numbers here converging to x. So in the inverse limit, I have the 3 points. These sequences are points in the inverse limit. So in the inverse limit, I have the 3 points. If I only consider the maximal points, so if I have this point and the point consisting only on the left part of these numbers and the one consisting on the right part of these numbers, if I only consider the maximal ones, so the one that contains all, this subset is homeomorphic to our original space. So we can detect explicitly our space in the inverse limit. It's just the subset of maximal points. And the previous works that we have in finite approximations are by Emily Kleider, that shown that every compact polyhedron has the homotopy type of an inverse limit of an inverse sequence of finite spaces. So she shown that the same result, but for compact polyhedra. So we were trying to generalize this, and we get this for every compact metric space. And also we found some results of Cooperman et al. That every compact Hausdorff space is the Hausdorff reflection of the inverse limit of an inverse system of finite spaces. So this is more general in the sense that is for every compact Hausdorff space. But the problem here, as they say in there, is the Hausdorff reflection. The Hausdorff reflection is kind of dark because it's like a black box in which you don't know what you are really doing. So we trying to clarify a little bit this. We shown that the Hausdorff reflection preserves the shape type. So in our construction, the set of maximal points actually is the Hausdorff reflection of our inverse limit. So we were also working without knowing it with the Hausdorff reflection of our space. And yeah, these two works are the ones that has these results. And that's it. Thank you.
I suggest we all unmute to thank Diego for his talk. Are there any questions or comments?
I have a question.
Go ahead, please.
Okay, so for, let's say a compact metric space X is given and epsilon is given too. But there's no canonical way to choose the finite approximation A, right?
No, there is not. Actually, you can use any finite approximation.
Okay. Then let's say A and A prime are the finite approximation for a given epsilon. Of course, they can be different. And do we have any relationship between those, the U induced from A and U induced from A prime?
Yeah, actually, so you can choose any approximation you want, satisfying the properties I said. And the thing is that there is no canonical way of doing it. The construction is general so you can choose any approximation, and the next step, any approximation, and you have the same results. In the limit, you have the same result. You have the same properties for the inverse limit. It doesn't matter what approximation you take. You can show, I mean, there is some result you can show that as inverse sequences, they are isomorphic in some sense. So in the end, you are doing the same construction, but in the inverse limit, you obtain different spaces, but all of them are has the same homotopy type that your original space. So I don't know if that's
okay. Ultimately, it doesn't matter. Okay. Thank you.
Okay, thank you.
Diego, I had a question on slide 37 or so. Right, so here you were constructing, an inverse limit where you were in sort of the category of finite topological spaces, right? So you had an epsilon and your U2 epsilon of A had, all finite sets of diameter most epsilon, right? So I mean, you explained well that you could have instead done a Rips complex or a Cech complex, right? But this feels very much like a Rips complex. When you turn this finite topological space into a simplicial complex in the sense of McCord, do you get the Rips complex on the nose?
You exactly get the
barycentric subdivision.
Yeah, exactly. Yes.
Okay.
Yes. Exactly. You actually get the barycentric subdivision, and the way actually we show that this preserves the shape is that you are detecting the shape is with an isomorphism with the Vietros-Rips sequence with all the points of a space, which is, but yes, you get this complex.
Thanks.
Thank you.
So Diego, could you explain what is a Hausdorff reflection that you alluded to at the end of the talk?
The Hausdorff, yeah. Yeah, here, yeah, the Hausdorff reflection is when you have a space that is not Hausdorff, is the smallest possible Hausdorff space that you can construct with the universal property that you have an inclusion of the space. So I tried to find some papers or books for this, and it was very difficult for me. So I find one that was in which is explained explicitly how to construct it. And it's not just, I was thinking about something like consider an equivalence relation, like if 2 points should be identified, just identified and then, so like a quotient. And it's not just this, it's more. You have to do the construction in 3 steps using a universal property for functions. So that's why I say this is very dark. It's not just a quotient of points of the space, you know, by equivalent relationship. So it's very hard to work with this Hausdorff reflection. It is.
Are there any more questions or comments?
I have another question. So I wasn't sure if I understood you correctly, but when you described, you know, shapes or the shape of a space or shape theory, you know, you constructed it using an inverse limit. And then you said something that made me think that this wasn't how Borsuk originally defined it, that it was just equivalent to that. So was the definition you gave really Borsuk's original definition, or is it a modern reinterpretation of his original definition?
Yeah, the original description of Borsuk is this one that I told you, is which is really, really, really hard. I mean, the paper in which Borsuk describes this is hard to read, and it's not very, I mean, you see some geometry, but the technical stuff that you need to understand or to prove or to show is very heavy and very not clear. So so the thing is that very geometrical, and the way Borsuk explains is very geometrical, but when you go to define the morphisms is something awful. So I'm very hard. And this inverse limits description is by Mardesik and Segal. So they are, I think Mardesik was the student of Borsuk. So the problem with the Borsuk definition is that this was very hard to generalize. There were some generalization with, I think, Ralph Fox did some generalization for metric spaces, also very hard to work with. And then Mardesik and Segal tried to do something more, an approach more, in which you can compute things easily. So the inverse limit approach is by Mardesik and Segal, and they have a book. And in this book is everything is, I mean, in the end, they are able, it's also not very satisfactory in the way that is very, is difficult to define properly, but it's better than the other theory. But in this way, you can define shape for arbitrary topological spaces, which is very nice. But you have to define maps between sequences and equivalent and relationship between them, and homotopy. I mean, you have to do several steps until you get a category that exactly detects the same as Borsuk's for compact metrics and generalize properly.
Thanks so much.
Thank you.
Are there any more questions? Okay, if not, let's thank Diego again, and I will stop recording now. So.